Hello students, today in this lecture we are going to solve some problems using beta function, and then we will use some transformation property of the beta function. So let's start it. The first problem is to evaluate the integral. This is the problem. Evaluate the integral, which is the integral from 0 to 1 x to the power 4 into 1 minus x to the power x under root whole to the power 5 into dx. So solution. Let us consider this x under root to be equal to t, or this implies that x is equal to t square, taking square to both sides, and then taking the derivative of this x will be equal to dx is equal to 2t dt. Now substitute these values in the above integral, then the integral which is given to us is this integral from 0 to 1 x to the power 4 into 1 minus x under the root whole to the power 5 dx will be equal to, which is here we have x and x is t square, so t square whole to the power this is integral from 0 to 1 whole to the power 4 into 1 minus x under the root, which is t to the power 5, and dx is 2t dt. Now this will be equal to integral from 0 to 1 and t to the power 8 and 1 minus t to the power whole 5 into 2t dt. Bring this 2 out of the integral, and this will be 2 times integral 0 to 1 t to the power 9 into 1 minus t to the power 5 dt. Now look at the beta integral, which is beta lm is equal to integral from 0 to 1 x to the power l minus 1 into 1 minus x to the power m minus 1 into dx. Now look here to this integral and this one, which is this can be written as 2 times integral 0 to 1 t to the power, I can write it as 10 minus 1, and this can be written as 1 minus t to the power 6 minus 1 dt. Now look these two integrals. Here we have L, here in this integral we have a variable x, but here we have variable t, so it doesn't matter. Look here, we have L, but here we have 10. Now here we have m and here we have 6, so we can write it as 2 times beta 10 6. This is the beta 10 6. And Further we can write it as 2 times gamma 10 gamma 6 upon gamma 10 plus 6. As we know, the property of beta function which we discussed in the previous lecture was beta lm. This can be written as gamma l times gamma m divided by gamma l plus m, which is in the previous lecture. So I have used this property here. So I can write it as 2 times gamma 10 gamma 6 upon gamma 16. And now we can write it as 2 times 9 factorial, and this can be written as 5 factorial, and in the denominator we can write this gamma 16 as 15 factorial. As we have a property of the gamma function where you guys know that gamma n plus 1 can be written as n factorial. Clear? So further this can be written as 2 times 9 factorial 5 factorial divided by, if I expand this factorial up to 10, that is 15 times 14 times 13 times 12 times 11 times 10, and similarly up to the rest we can write as 9 factorial. There is series from 9 up to 1, we can write it as in 9 factorial. So I can cancel this 9 factorial with this 9 factorial, and the rest can be written as 2 times 5 factorial can be written as 5 4 3 2 1 divided by 15 14 13 12 11 and 10. Now by simplifying this we can get this is actually 1 upon 15,015. So this is the result of the integral which we had evaluated, x to the power 4 into 1 minus x under the root whole to the power 5 dx. So this is the result. Now another problem, which is is evaluate the integral which is from 0 to 1 minus x cube whole to the power negative 1 over 2 into dx. So the solution is, now let x cube is equal to, that is y, or this implies that x will be equal to y to the power 1 over 3, and then dx will be equal to 1 upon 3 y to the power, so this is 1 over 3 minus 1 will be minus 2 over 3 into dy. So whenever, remember students, whenever we are making some substitution, so we have to check the new limits of the integral. Here in terms of y, the limits of x here in this integral was from 0 to 1. So here if x is equal to 0, then y will be equal to 0, and when x equals to 1, then y will be equal to 1. So there is no change in limits. So no change in limits. So we can proceed now. Therefore, the integral which was 0 to 1 into 1 minus x cube whole to the power minus 1 over 2 dx, this can be written as integral from 0 to 1 into 1 minus x cube is y whole to the power minus 1 over 2, and dx is 1 upon 3 y to the power minus 2 over 3 into dy. Now I can further write it as, bring this 1 over 3 out of the integral, so this will be 1 upon 3 into integral from 0 to 1, and this will be y to the power minus 2 upon 3, and then this value which is 1 minus y to the power minus 1 over 2 into dy. So guys, I can write it as 1 upon 3 into integral 0 to 1, and if I write this y to the power minus 2 upon 3 as y to the power y to the power 1 upon 3 minus 1, y to the power 1 upon 3 minus 1, right? And so there is no change. If you subtract minus 1, if you subtract 1 from 1 over 3, so you will get minus 2 over 3. So, and I can write this 1 minus y whole to the power minus 1 over 2 as 1 over 2 minus 1. Clear? And dy. So this is now the beta function of 1 over 3 and 1 over 2. So this is 1 upon 3 beta 1 over 3 1 over 2. Clear? And by using the property of beta and gamma function, that is 1 upon 3, and this is gamma 1 over 3, gamma half, and this is gamma 1 over 3 plus 1 over 2. Clear? And by simplifying it, I can write it as 1 over 3 1 over 3, and this gamma half is actually under the root phi, which was already done in the gamma function, and this will be gamma 1 over 3 upon gamma 5 over 6. So this is the answer. Now in the next we are going to discuss the transformation of beta function. Transformation of beta function. That means that to show that, or to show that beta Lm can be written as integral from 0 to infinity x to the power m minus 1 upon 1 plus x whole to the power m plus l into dx, or we can write it as in this form: integral from 0 to infinity x to the power l minus 1 upon 1 plus x whole to the power l plus m into dx. So we have to prove that beta function can also be written in this form. So this is also the beta function. Now proof. So by definition of beta function, by definition of beta function, that is beta lm can be written as integral from 0 to 1. Here the limits are from 0 to 1, and x to the power l minus 1 into 1 minus x to the power m minus 1 into dx. And we must remember that these are actually real numbers. Let put x equals to 1 upon 1 plus y. So this will lead us that dx can be written as, so the derivative of this will be minus 1 upon 1 plus y whole square into dy. So again we have made some substitution, so we have to check the limits, either these are changed or not. So for limits we have made substitution here. So solving this equation for y as 1 plus y will be equal to 1 upon x, bringing this 1 plus y to the left, and x will be come to the denominator, and y will be equal to 1 upon x minus 1. So if you put the existing limits here for x, we will get the new limits. When for lower limit, when x equals to 0, then 1 upon 0, which is infinity. This means that y will be equal to infinity. And when, so this is the lower limit, the lower limit, our new limit will be infinity. And when x equals to 1, so substituting x equals to 1 here, so we will get y equals to 0. This is the upper limit. So now if we are making this substitution here in this integral, so we have to use these limits now. So therefore beta lm can be written as integral from infinity to 0, and x will be written as 1 upon one plus y whole to the power l minus 1. And here this will be 1 minus x. X is again 1 upon 1 plus y whole to the power m minus 1. And dx will be written as minus 1 upon 1 plus y whole square into dy. So making some simplifications, this negative sign will be brought here, and it will change the limits, it will invert the limits. So this will be 0 to infinity, and here we have 1 upon 1 plus y. So anything to the power 1 will be again equal to 1. So if we apply this power to the numerator, it will give us 1, and here in the denominator it will be L minus 1. And similarly, for this case, it will be taking the LCM of these two. If we will get y to the power m minus 1 upon 1 plus y whole to the power n minus 1, m minus 1, and this will be dy upon 1 plus y whole square. Now this will be now equal to integral from 0 to infinity y to the power, here in the numerator we have m minus 1 divided by, here is 1 plus y, 1 plus y, 1 plus y. So all these powers will be added to 1 plus y whole to the power L minus 1, L minus 1 plus m minus 1 plus 2. So this 2 will cancel with this minus 1 and minus 1. So we will be only left with L plus m and dy. So now the property, by using the property of definite integral, is there is, we can write an integral from a to b f of x dx as integral from a to b f of y into dy. So there is no change for in the result of the integral for the variable. So replace this y by x, we can write it as integral from 0 to infinity x to the power m minus 1 upon 1 plus x whole to the power m plus l or l plus m and dx. So this is the beta lm. So this is the first result which we have proved, and we are asked to find beta lm, and in this form, that is x to the power m minus 1 divided by 1 plus x whole to the power m plus l into dx, which is our result here. And now, yesterday we had a property which we had, that beta lm can also be written as beta ml. So everywhere, if in this integral we have m, replace it by l and interchange these limits. So therefore integral from 0 to infinity beta lm infinity x to the power m minus 1 upon 1 plus x whole to the power m plus l into dx. This can also be written as integral from 0 to infinity x to the power l minus 1 upon 1 plus x whole to the power l plus m into dx. So this is beta lm and this one is beta ml. Okay, this is the result.